and welcome to another session with the R User Group community. So please, on the chat of the call, can you tell us where you are joining us from, and we can say hello to you. So my name is Adira Lawal, and I'm going to be your host for today's meetup. So what we are going, I'm going to intro our agenda so we can meet everyone. So welcoming participants and welcome everyone. Welcome, welcome. It's good to have you here with us. Next, we'll be talking about the R User Group community, the meetup repetition organizers, and the meetup generally. So, about the University of Arizona Group, our mission is to foster the use of R in data analytics, data science, and impactful application across diverse fields such as business, health, and research. So, whether you are starting fresh or you're an experienced professional, this unique opportunities to connect with other fellow enthusiasts that are new to this, share knowledge, and deepen your understanding of data science. At the Arizona Group community or group, we aim to boost and reinforce the community of data science and artificial intelligence and machine learning professionals and academics through collaboration, mentorship, seminars, training, and conferences. And we are committed to nurture talents, driving innovation, and these fields. Let's embark on this journey in the world of art together. So, how do you join us? We have to do this. We're going to copy this link and send to the chat of the call, and um, we would have people to, if you're not on that group, you can always join that group. So welcome, welcome, welcome everyone. So we want to say thank you to everyone for joining and welcome once again. So on the chat of the call, please tell us where you are joining us from so we can say hello to you. So let me start with myself. My name is Adira Lawal and I am joining from Oyo State in Ibadan. I'm so Oyo State, Ibadan to be precise in Oyo State. Okay, so let me check the chat on the call. Who else is joining? So let me see. Adiola Lawal. I'm joining from Ibadan, Oyo State, and I'm going to put Nigeria there. So I'm also joining from Nigeria. So please tell us where you are joining us from. To those online, thank you for joining us and welcome. Also on the chat of the call, tell us where you are joining us from so we can say a big welcome to you. Okay. Please, I'm waiting for one or two people to tell us where they are joining us from. Okay, so we have Chinoye joining us from Port Harcourt. Port Harcourt is in Nigeria too. Nice meeting you, Chinoye. Let's see, who else? Who else? GBG, where are you joining us from? I think I saw who else? Garba, where are you joining us from? Mr. Kosim, where are you joining us from? And Professor Gafar, please, where are you joining us from? Professor Gafar, Professor Garba, tell us where you are joining us from. And Professor Garba, tell us where you are joining us from. Oh, Kasim is joining us from Kwara State, Nigeria. Thank you. Prof, we're waiting for you. Where are you joining us from, sir?
Thank you. Good morning.
Yes, sir.
Joining you from Ilorin, Kwara State, Nigeria. Thank you.
Oh, nice. Thank you for joining us. Dr. Garba, where are you? Oh, Professor Garba, where are you joining us from?
Hello, Adeola. You are well done. You are doing well. You are making us proud. I'm Dr. Mohamed Kadir Garba. I'm joining from University of Ilorin, Kwara State, Nigeria. Thank you for doing
Nice to see you. Thank you. Okay, so we have Adeni here from Ilorin, Kwara State, Nigeria also. Thank you. All right. Thank you everyone for joining. And we promise today is going to be a great time with the professor. So we are here to learn and to ask as many questions as they want. So I'm going to be sending the link to the Ariza group chat of the call and online. So for those that are not joining us, you can always join us there. So currently we have over 900 plus members of the community. So you can always go there, ask your questions as much as possible, and there will be someone that will definitely have answers for you. If you have any questions, you can ask, and please and please let's be polite with our questions and polite with our answers. It's very, very important. Thank you. So moving on, moving on, that is how to join us. So we'll be meeting our user group organizers. We have Dr. Garuba, what I was saying, to tell us where you're joining us from, is our host. Then I am Adira Lawal, I'm your co-host. Then Mr. Ezekiel Diko is the co-host, and Dr. Faron, who also also our co-host for today. So you can see any of these faces. You can always chat them up on Meetup or see them anywhere and ask your questions as much as possible about the community generally. So we have a code of conduct. There's no community without rules. So our expected behaviors are all participants are going to treat everyone with respect, courtesy, and consideration, honor different viewpoints and experiences, avoid demeaning, discriminatory, or harassing behavior and speech. So let's speak politely with everyone. Unaccepted behaviors, harassment and abusive behavior will not be tolerated, including but not limited to one, offensive comments or insults related to gender, sexual orientation, disability, race, age, religion, appearance, or any form of other protected characteristics. You have people from different races joining us, so we don't want to discriminate among anybody. Deliberate intimidation, stalking or following, harassing photography or recording without consent, inappropriate physical contact or sexual, imaginary, or sustained disruption of talks when the speaker is speaking. So if the speaker is speaking, please let's keep all our questions to the end of the call, or you drop it on the chat of the call. We will always have a response for you. So who are we meeting today? We are here talking about the introduction to multivariate analytics techniques using R, and who will be taking us is going to be Professor Gafar M. Oyeyemi. Apologies if I did not pronounce this correctly. He is a professor of statistics, and we are here to meet Professor Gafar. So Professor Gafar Matomi Oyeyemi is a professor of statistics specializing in multivariate analytics and data science at the University of Ilorin. He obtained his BSc, MSc, and PhD degree in statistics in 1998, 2023, and 2029, respectively, and became a professor in statistics in 2019. He has supervised numerous undergraduate projects with over 30 MSc dissertations and 15 PhD theses, with 80 plus scholar publications in reputable journals. I'm clapping for you, sir. Beyond academia, Professor Yemi has served as a consultant to the Universal Basic Education Commission, the National Agency for Food and Drug Administration, that's NAFDAC, and KPMG Nigeria. And as a resource person for capacity building in startups, SPSS and R, he serves as the head department of statistics from 2021 to 2024, and is currently the general secretary of the OFA, Professors Forum, OPM. Nice meeting you, sir, and thank you for joining us. Please round of applause because that section is quite good. Prof, please, I'll be using Prof for you, first. It's good to have you join us, and we're here to learn from you as much as possible. Thank you, sir. And
Thank you, Adiola.
Yes, sir. Over to you, sir.
Thank you, Adiola and others. Thank you.
Prof, are you
Hello,
still
can
with
you
us?
see my screen?
Oh, not yet,
Yes.
sir. Okay, it's coming up. Oh, yes, we can. Yes, sir.
All right. Thank you. Good morning, afternoon, or whatever the day is to our listener. As the co-host or the host has said, my name is Professor Gafar Matami Oyeyemi from Department of Statistics, University of Ilorin. I will be speaking to introduction to multivariate techniques using R. And I will take us through a little bit of theory and multivariate techniques before we go to practical session. But let me start by appreciating the team of R User Group, UNILORIN R User Group. The chief host, Professor Garba, and the others. Well done for that wonderful job. The content of this talk this morning will dwell on what is multivariate analysis. Why do we even have to do multivariate analysis? Then we are going to look at techniques, some, not all, of multivariate analysis. So we look at maybe one or two theoretical illustration of the techniques before we go into practical session. Can you hear me? Hope I'm on.
Oh, yes, yes, sir, you are on, sir.
Thank you. So starting with multivariate analysis. And summary, multivariate analysis is just about exploring or looking at the relationship that may exist among many variables. The difference between multivariate analysis and other area of statistics is that in multivariate analysis,
Prof,
we
sir. Sorry.
simultaneously looking
Prof,
at,
sir. Can you use the
yes,
slideshow so that we can see it clearly and boldly? Slideshow, sir.
okay. Um,
Thank you, sir.
Thank you.
Thank you, sir.
I was trying to define what multivariate analysis is, and I was saying that it's just when we are interested in looking at or exploring relationship that may exist among many variables. And I say many variables, we're talking about batteries of variables. But the simplest one is when you just have two variables that are of interest to us. And we call them dependent variables. So we want to maybe look at the pattern, the relationship, and so on and so forth. They are so complex, but that's just the brief definition of multivariate analysis. Among the objectives of this technique or this field of statistics is to identify any pattern or sub-pattern and correlations that may exist among our observed variables. As I've said, we are having many variables. Two, we may want to understand relationship among or between these variables. Then it could be to estimate or test some hypotheses about the population parameters, just as we have for univariate case. Then for prediction of outcomes. And then finally, cluster classification and clustering analysis. So the multivariate can be grouped into three types. The first being descriptive multivariate techniques. The second is inferential multivariate analysis, while the third one is predictive multivariate analysis. And I'm going to look at each one of these types. So under the descriptive, this is where we'll be dealing with principal component analysis, factor analysis, cluster analysis, among others. They are all about describing the nature of our complex data, that is multivariate data. So we talk about PCA, factor analysis, and cluster analysis. The second type is when we talk about inferential multivariate analysis. And this is when we'll be dealing with estimation, estimation and test of hypothesis, discriminant and classification analysis, and canonical correlation analysis. While the third type or the third category is when we be dealing with a multivariate regression model, then decision tree, and random forest. For this particular session, I'm taking us back to the inferential. So we'll be looking at test of hypothesis and discriminant or classification analysis. That is what our practical session will dwell with. But just let me quickly take us through some theory of these two distinct analysis that I said that we are going to deal with. When we talk of type of test of hypothesis, we have three groups or three categories of sorts. This is when we have just one sample, or the second one is when we have two groups or two samples. Then the third one is when we have more than two groups or two samples. Remember, unlike a univariate, in which we just test about just one response variable, this time around in multivariate, we are testing about vector of means. So the mean could be 2, could be 3, could be 10, could be 20. What we know that our P, the response variable, is 2 or more. So when we have two or more variables, as I've said earlier on, we are dealing with multivariate analysis. under each one of them, we look at some the test statistics. So under one sample case, these are the assumptions. We assume that the sample is from multivariate normal as given, and our variance covariance matrix must be positive definite. Then we talk about large sample, that is, the sample size must be definitely be greater than P. That is, the number of observations is expected to be more than the number of dependent variables or responsible that you are dealing with. And here is the hypothesis. So the eighth note is that the mean factor is equal to the factor or a factor of constants. The mean factor is a factor of constants. So against the alternative that is not equal to factor of constant. And the test statistics are just two. If the variance covariance matrix is known, the sigma, then the test statistics are shown will follow chi-square distribution with p degrees of freedom. But if the sigma, the population variance covariance matrix is unknown, so such population variance covariance is estimated by sample variance covariance matrix known as S. So the test statistics follow Hotelin square distribution with p, n minus 1 degrees of freedom. Then for two sample or two groups case, and here is the test hypothesis, the eighth note, so that the factor of mean for group 1 is equal to the factor of mean for the second group. You know, I told us that in this case, we just have two groups or two populations. So the factor of mean, so this factor of mean, the mean could be 2, could be 3, could be 4, could be p of them. So it's equal to the factor of mean for the second group against the alternative, or which is sorry, the editing there supposed to be 8-1, not 8-0. So the test statistics is as shown, and it follows alternative square distribution with p comma n plus 1 plus n1 plus n2 minus 2 degrees of freedom. My SP there would be the pool variance covariance matrix. That is, we are going to pool the two variance covariance matrices as shown, and we get the known hypothesis if what we computed is greater than the table value. Then, lastly, testing of factor of mean is when we have more than two groups or sample. So here we'll be talking about what we refer to as multivariate analysis of variance, which is multivariate equivalent of ANOVA that we are all familiar with. And the above is the model, and we have the hypothesis. The hypothesis can be in two forms. The first form, hello, am I online? Adiola? Hello?
Go ahead, sir. Go ahead, sir.
Yes, sir, you are with us.
Thank you.
Yes, sir, we are here, sir. Can hear you clearly.
Thank you. The first form of
We can hear you,
hypothesis
sir.
as shown is when we are, yes, sir, yes, when we are testing that the factor of mean for G groups are equal against the alternative that they are not equal. While the second one, the second form, is when we are applying multivariate to the design of experiments in which we are testing that the factor of treatment is equal to for group 1 is equal to that of group 2 equals 0. So the second one is specifically used when we are applying multivariate analysis to design of experiment or experimental design. So for those that in experimental design, they will easily get it because we are testing that the effects, the treatment effects is for each groups are not different from one another, and they are not different from 0. And the test statistics is as given. So you have that F, and where lambda is as given. So the lambda is what we call a Weeks lambda, and is the ratio of a determinant of what we can refer to as sum of square error matrix over the sum of square error matrix plus the sum of square for treatment effects. So we have that as lambda. Now, the second area we are going to look into in one of the techniques is discriminant and classification analysis. So we look at what is discriminant analysis. Discriminant analysis is just a way of describing or separating difference between two or more groups. When we try to describe that, given a set of observations, we can describe them that they belong to different groups. So the other thing that discriminant analysis does is that it identifies the relative contributions of variables and the separation of these groups. So when we have classification variables, maybe P of them, we'll be able to see the magnitude, either small or large, or even the direction, either positive or negative, of each of these variables, how they are contributing to this discriminant analysis. Very soon, when we get to the practical session, we'll see such. Then it finds the optimal plane that best illustrates group configurations. Then from there, we move to classification analysis. The reason why I separate the two is that in some tests, the two are always treated together, but they are not really the same, because where the discriminant analysis ends, that is where classification analysis starts. After getting the plane, the function that discriminates, so the process of applying that function in classifying objects into this group or the other group is what we refer to as classification analysis. And that is why I try to separate the two. So classification analysis assigns or allocates observed individuals to their respective groups. Then it also validates discriminant analysis using some criteria. So it is under classification analysis that we are going to validate how good, how accurate the discriminant analysis we obtain is, before we can say, okay, because of the high accuracy, this discriminant function is good. Then let's look at discriminant analysis. We are going to look at the linear one, what we refer to as linear discriminant analysis. We have quadratic, we even have robust discriminant analysis and so on, or what we call regularized discriminant analysis, but we will limit ourselves to linear as well as quadratic discriminant analysis in this practical session. The major assumptions is that we expect our data to be multivariate normal. Then the groups have common or the same variance covariance matrix. This assumption is germane for linear discriminant analysis. It's very germane. The moment that condition or assumption breaks down, the LDA also breaks down. Then we look at that the number of variables is less than the sample size. Then we also have distinct main factors, say mu1, mu2 up to mu-g. We say that note that data matrices from each groups of population have p variables. So looking at linear function now, what we refer to as LDA. So a linear is a linear combination of the p variables. These p variables are discriminant or classification variables. So it maximizes the distance between population's main factor. So that function tries to maximize the distance between or among main factors that of groups that we may have. It also transforms each observed factor to a scalar. I'm going to illustrate such soon in the next slide. So the formula is as given, so in matrix form and as well as in vector form as we have. Now, assuming we have this data matrix, we are going to say we have two populations. Forgive me for that error. It should be population 1, population 2, not population 1, population 1. So it's editing issue. So we have that data matrix for population 1 and data matrix for population 2. The linear discriminant function will transform this vector of matrix into scalar, just as we have seen. So we have population 1, we have our Z1 to be equal to that, then population 2, and we have our Z2 to be equal to that. We get it much better when I show you this data matrix. Assuming you have this data matrix for population 1, as you can see, our P is 3. We have 3 classification variables, and those are the observations. Then population 2, we have sorts. We may have more than 3 variables. It could be 10, it could be 20, depending on the nature of our data. You now see the second column, which we call scalar for set 1. It has transformed the vector into a scalar for each of the observed vector. So that is one of the functions of the that linear function. Is going to transform our observed vector into a scalar for easy classification of individual observations, individual objects. So you see that it's more easier working with scalar, as we have seen, than working with the vector of observations. So, and this is how we obtain that transform or linear function. So the linear function, as I have seen, we said is A transpose x bar 1 for Z1. For Z2 is as that. So we now try to find the vector A, the value for vector A. And the vector A, the value is obtained so that the Z, that linear function, will maximize the difference or the distance between the two groups. Remember, we are just talking about two groups, two populations. So it could be more than two populations, as the case may be. So with the standardization of the difference between the distance, we obtain our the value of A that maximizes the distance is as given. Is going to be the inverse of the pooled freedom covariance matrix multiplied by the difference between the two main vectors, as we have seen. And the classification procedure is as follows. So we are going to say that get the mean for Z1, the mean for Z2. So we take the difference, we take the average of the two. So that average of the two becomes our cutoff. So when we observe our vector of observations, we convert that vector of observation into a scalar, which we are called Z. So that Z will be compared with the that cutoff. So if Z is greater than that cutoff, that observed vector will be classified to be population 1 and into population 2 if otherwise. So this is the procedure of assigning individual objects into their respective groups. So individual objects, we are going to observe a vector of observations. That vector of observations will be converted to scalar, and that scalar will now be compared with the cutoff. Is it greater than the cutoff? Fine. If it's greater than the cutoff, that's observed vector of objects, let's say I, will now be assigned to otherwise it will be assigned to population 2. With this the theory, the theoretical background of what we are going to be treating in our practical, so that to certain extent we are going to have and factors. We are going to consider 1 sample case, 2 sample case, and 3 sample case, as I've said. So we do a little of what we call simulation study to look at or demonstrate the effect of dimension, that is the number of variables, as well as the sample size on the alternative square of a thing. When we are done with that graphic discriminant, look at the performances of the LDA, which is the linear discriminant analysis, the QDA, the quadratic, and compare them with even the logistics because at times we do use logistics to classify objects as well. So I'm going to take us to R in the next few seconds so that we begin the practical aspect of the talk. Just give me a few seconds.
Thank you so much, sir. If you have any questions, please let's drop our questions in the chat so we can ask Professor Grafa before he comes up with the RCU presentation. Please, if you have a question, drop it in the chat and we'll read it out to you.
Thank you, Adiola. Well, unfortunately, my art studio, my laptop that I supposed to have used that as an art studio is not behaving well. So this one, I'm just going to be using R to illustrate some of what I've just explained in theory. And for everyone, every R we have, we'll be using iris data. We'll be using iris data. And the other aspects we'll be using goes through simulation. So we don't need to load any package or what have you. And I believe that the moment we install our R, it's going to have the package mass, MES, as well as the data that comes with it. So the first thing that I will be taking us through, as I've said, is the test about factor of mean. Hope you can see my slide. So I need to first load these two package MV test. Let me quickly download the package. It's not in this. Just give me 1 minute to quickly upload, download the MV test from. I'm sorry for that. Which one should I use?
So, Mustafa, please, can you mute your mic?
I'm sorry for that little delay. I thought I've downloaded that package. So for some of us that are online, that are following, you are going to need that MV test. So if you can quickly download that. Sorry, oh my God. I thought I have it. I thought I have it on this system. It failed again. Okay. Let's take ourselves through the second content, the second practical that I prepared for us. And that's about discriminant and classification analysis. So we are going to see, as I've said, use iris data. We are going to use iris data. Let me load the data. So let me just show us what iris data is all about. As you have seen, we have what I call four classification variables: sepal length, sepal width, petal length, and a petal width. So, and these are what we call the measurable characteristics of a particular flower, which we call the SEPA, or particular plant. So assuming as a biologist or sociologist or the agricultural student, what have you, so you want to use these characteristics to classify these your plants into 3 species, because we have 3 species for our those plants. We have Setosas, we have the other 2 groups, and we want to use discriminant analysis to illustrate that. This data, let's look at the dimension. It has 150 observations. It has 150 observations and 5 variables. The first 4 variables are what I refer to as classification variables, while the last variable, which is the last column, as we have seen, is the groups or the populations. Is the groups or the population. So if we want to see that, so we can try to see what that is. So the levels of those, or the categories of the populations, are Setosa, that's the first group or the first population. First color, that's the second one. The third one is Vaginica. So that's what constitutes the populations. So as a biologist, we want to classify these plants into these what do you call it, populations. So we can use linear discriminant analysis, and we are going to demonstrate such using both linear and quadratic discriminant analysis. Not only that, we will compare the results of the 2. That is, how good are the 2 in classifying these plants into their respective groups. So I start by saying we first look at we try to sample. We don't want to use all the 150 observations. So I create a sample. So this sample will sample just 75 from those 150 plants. So that is creation of the sample. Then the first group, 75, will be, I will call it trained data. I want to use that sample to train my model, while the second one will be used to test how good my model is. So this line, we extract the first, the first group, which I will call the trained data, while the other one we call the test data, as I'm extracting it. As I'm extracting it here, so we have 2 sets of data now: trained data and test data. So we the first data, which I call the first set of data, I've extracted 75 observations or 75 plants from that 150, while the second set of data is using the remaining one as a test data. So which I will use in testing how good the model that I fit is. So the command to fit the model is just fit. I call that function, I call it fit underscore LDA to distinguish it from the other one. And the command is LDA. LDA stands for linear discriminant analysis. So I will provide the species, which is my classification variables or grouping variables, will stand as my dependent variable, as if I'm writing a model, say y equals x1, x2 plus x3, and so on. So this first argument here is representing the grouping variables. And this sign, the wavelength sign, means equal for those that are very good in R. So this sign mean equal, that wavelength sign mean equal. Then instead of specifying separate length, separate width, and so on, I don't to save time. I'll just put dots. So that dot means that it's going to take all the remaining variables as my classification variables, then comma. So the data that I want to use is train data, as I've said, train data. So the first is 75 observation that I extracted. So that's what is going to use as the train data. So with this, I've fitted a linear discriminant analysis for that data. So the next thing that will change if I want to use quadratic is just change that LDA to QDA. With this, I've instructed the R to fit a quadratic discriminant analysis to that my set of data, which I call train data. So I've fitted the quadratic with this function QDA into what we have there. As I've said, the specific stand for the response variable or classification variable, while that wavelength line sign means equal, then I don't need to specify all those 4, 5 classification variables. I'll just say dot. That dot represents that all other variables except the first one that I've specified, which is summary. I want to see the summary statistics. Say summary, which is FIT, all that is used, the count, the mean, the fit LDA, and I have this the output as we have seen. So we have the prior. The prior that is used is that is taking or is assuming that each of these groups is having the same number of observations in that trained data. So that is when you can use, that is by default, that is what the R used. So use the default. It use probabilities, that is the percentage or the proportion of each of these groups in that sample. That is what we use as a probability. As you can see, we have setosas having the probability of 0.37. That means 37% of that sample of 75 belongs to or have setosas as observation, where versicolor has 30% or 33% of 75 of the 75 as the number of observations, while Virginica has approximately 30% of that sample size of 75, as you have seen. Now, it's the next thing is the group means, as you have just seen. So we have for this all the four classification variables. So you have for each of the group, you have the means for each one of them. Because it is this mean factor, as I've illustrated in the theory, that is going to be used in getting the cutoff. So as you have seen, assuming we have just two groups, so we would have stopped at setosa and fasciculum. So it's going to find the mean for these two groups and use the average as the cutoff. Now, for the coefficient of linear discriminant function, as I've told us that when getting our Z, this one represents our Z1, L1, L2, that is the linear discriminant function. Because in the theoretical example I gave us, because we are having two groups, we are going to have just one linear discriminant function. But when we have three groups rather, we are going to have two linear discriminant function, because this discriminant function is what is going to use in the classification of the observations that we have. To appreciate what the table that we have, so we can get what I will call the classification table for, that is, I fitted the model. Now I now want to use the model to classify the remaining 75 observations using that model. So I have this table that I want to use. I call it table 1. So this table 1, let me first predict before I get the table. So I will say I want to predict. So this command we predict, that is going to apply that model onto the remaining 75 observations and use it to classify those 75 into the 3 groups: the setosas, the vaginica, as well as the fasciculum. So, and if I say predict 1, if I call it out, so we have, sorry, instead of saying predict, I will call it table 1. So if I say table 1, object table 1 not found, I think we have problems somewhere. Just give me a minute. I fitted the model. Edit. Okay. So this will give us the prediction, but this actually is not what I actually need. So what I need is the classification itself. So to call the classification, I'll just put this string behind it to let me know that, or to give me the class, not actually the classification values. So these are the classification that we have. It has classified that remaining 75 observations into their respective groups: setosa, fascicular, and then vaginica. But let's now compare it. That is, looking at the true value as well as the predicted value by cross-tabulate the actual prediction as well as the real value. So I will tabulate. So I will use function to tabulate this predicted value against the actual value. That is, this is the predicted class against the actual class of the data that I use. So if I now say table 1, so we are going to see the classification as we have seen. So you see that the diagonal entries are the correct classification, while all the off-diagonal entries are those that are wrongly classified. Like if you look at this setosa of a thing, so 9 of the setosa, if you add it across, you have 9 plus 10, that is 19 plus 9, that's 28. Out of the 28 observations that plants that are setosa, 9 of them are correctly classified, while 10 were wrongly misclassified as fascicular, and the remaining 9 were wrongly misclassified as vaginica. Ditto for fascicular. For fascicular, we have 8 plus 4, that is 12 plus 13, that is 25. So out of 25 fascicular plants, 8 were wrongly misclassified as setosa, while 4 were correctly classified, that are versicolor and correctly classified as versicolor, while 13 were wrongly misclassified as Virginica instead of versicolor. And finally, for the third group, we have 5 plus 11, that is 16 plus 6, that's 22. Out of 22 plants that are in that observation, 5 of them were wrongly misclassified as cetisola, 11 wrongly misclassified as versicolor, while only 6 were correctly classified as Virginica. So that is for LDA. So if you want to get the accuracy, that is how accurate, you know, the accuracy will be number of correct classification over the total number of observations. So we can use this command by just saying that we represent it with ACC, as I have it here. I don't want to be typing, that's why I'm copying and pasting. So we have this to sum all the diagonal elements and divide it by number of observations. So with that, we are going to get the percentage of classification correctly classified. So let's call it, so we have that to be this. So we have the level of accuracy for LDA to be 0.25. That is about 25% of the observation or the plants were actually correctly classified, while the remaining 75% were wrongly classified. So let's look at the other one, the QDA, that is the quadratic discriminant analysis. So we have this, and I want to get the predicted one and cross-tabulate it. I don't need to be repeating myself again. Let me just have the table of that one as well. So this table 2 is for the classification table, or what we call the confusion matrix for the classification analysis. So we have this one for the quadratic discriminant analysis. Just as I've explained, we have they have the same results as we have seen. They have the same results. The Setosa, the same thing for the LDA, the same thing, but this is just by chance. By the time we get to the simulation, we are going to have a better illustration of this one, of comparing the two. So that one will take us to looking at assuming we have I'm going to have a little simulation, so to speak, in which we want to compare if you have 2 groups or even K groups, but we are going to limit ourselves to just 2 groups now. And we are assuming that they have equal variance covariance matrix or different covariance matrix. That is, the 2 variance covariance matrices are not the same. So that is what this simulation is all about. Then we are going to look at the magnitude, or the what we call the number of variables that we'll be dealing with. So I'm going to copy this code, but I'm going to explain it line by line so that we are going to appreciate what the code is talking about. If you look at this code, I call it LDA underscore QDA. So the function has this following arguments. The row is just giving us the relationship that exists among the pairs of variables that we are going to deal with, either 3 variables, 4 variables, which are called P variables. Then the P stands for the number of variables that we have, what we call classification variables. While my M is the magnitude of difference between the 2 population variance covariance matrices. That is my M. My K is the sample that I'm going to use in a multiple of 10, maybe 20, sample size of 20, 30, 40, and so on, but multiple of 10 anyway. While Q is the fraction of number of observations in this group. That is, we have 2 groups. So if I want to use equal sample size for the 2 groups, So my Q would be 0.5. But if I say my Q is 0.4, that means for sample size, it has 4%, while, sorry, 40%, while the other group is having 60%. That is what the Q represents, as we have seen. So here, I try to have the sigma. As I've said, I'm trying to explain it line by line. The sigma 1 will represent the variance profile matrix for population 1, while sigma 2 will be population 1 variance profile matrix for population 1 multiplied by m. So if my m is 1, that means they have equal variance profile matrix. If my m is 2, that means the second group or the second population has 2 times variance profile matrix larger than the first population variance matrix. So having gotten that, so we have the data matrix for group 1. I represent my x1 to represent the data matrix for group 1. Then x2, the data matrix for group 2. That is the classification variables for group 1. Then the classification variables for group 2. They are going to have the same P anyway. Then combining them, I call them X. Then the group, that is, I'm trying to have the number of observations for each group. So for group 1, so I replicate it n1 times, and for group 2, which is 2, was replicated n2 times, in which I've defined my n1 to be my sample size multiplied by Q. So that is the proportion that my first population we have, while the remaining one, which is n2, will be n minus n1. So with that, after that, I fitted the model because I combined all the group, the data together to form the data frame, as I've seen. So then we fit the model for linear discriminant analysis, then for quadratic discriminant analysis. Then, as I've illustrated in the first practical, so we get the predicted value, then we do cross tabulation. After the cross tabulation of the predicted and actual value, we try to get the accuracy. That is by dividing the number of observations, the number of diagonal entry, the sum of it divided by the number of our observations. Then we have the output. Now, to recall this, to simulate, to just get the output for each of these functions, each of the arguments that I provided. So I'm going to say LDA underscore QDA, then provide the necessary arguments. The row, that is the, as I've told us, the level of relationship that exists between the pairs of my variable. Let's assume that the row is 0.8. So assuming the number of variables, let's say is, as I've said, let's start with 4. We have 4 grouping or classification variables. Then my n, the magnitude of difference between the variance covariance matrix for group 1 and the variance covariance matrix for group 2. As I've said, if my m is 1, so it means that the two variance covariance matrices are the same if my m is 1. But if my m is more than 1, maybe 2, maybe 3, just multiple of this thing, then it means that they are not the same. Then the k is, as I've said, is the step that I'm taking in multiple of 10, the sample size that I want. So if I put 20 now, so I'm going to have 20 different samples starting from 10, so and so on. Then starting from 20, 20, 30, and so on, as we are going to see very soon. So, but I'm going to have just 20 set of outputs in multiple of 10. Then the Q, as I've defined, is the proportion. If my sample size is 10, so that means I want to divide these 10 observations into 2 groups. Group 1, we have maybe 5 observations. Group 2, we have 5 observations. It means that my Q is 0.5. But if my Q is 0.4, group 1, we have 4 observations, while group 2, we have 6 observations. If my sample size is 10, as I've said, we are going to use multiple of 10 in our simulation. So here I'm using 0.4, so that group 1, we have 40% of my n, while group 2 we have 60% of my N. Then good. Some group is too small for QDA. I'm going to explain this. I will reduce my variables to 3. I will reduce my variable to 3 because if you could recollect, I said that my P, and when I was taking us through the theoretical approach, that the number of observations must be greater than P, the number of variables. Here, as I've said, my group 1, because my sample size will be 10 for the first simulation. So, and these 10 observations will be divided into 2 groups. So, as I've illustrated, as I have input, so 0.4, that is 40%, which is 4, will be for group 1, while 6 will be for group 2. Now, the group 1 that has 4 number of observations with 4 variables. So, the number of observations is equal to the number of variables. So, there is no way under QDA that the variance covariance matrix will be estimated. So, that is why it's giving error message here. But if I reduce the number of variables to 3, if I reduce the number of variables to 3, so let's see the output. So you can see the output when I reduce the number of variables to 3. That is, I have classification variable just 3, x1, x2, x3. So here, x3, that is 3 variables, is less than 4. The number of observations in group 1, as we have seen. For group 1, for the first simulation, the sample size is 10. That 10 number of observations is divided between the 2 groups. So group 1 has 4 observations, group 2 has 6 observations. So with this, my N, which is for group 1, it is 4, is greater than 3, which is number of observations. That is why we are having results. So here, we are comparing the 2 discriminant analysis, the linear and quadratic. The third column is for quadratic, while the second column is for linear. We can easily compare for various sample sizes, as we can see. So as the sample size increases, we're having the accuracy to be getting smaller and smaller and smaller. But in all cases, it seems that the QDA, the quadratic discriminant analysis, performing better than the linear in most cases, except towards the tail end or the last one when we are having 20 observations. But this simulation is done just once. It's just once. When it takes these 10 observations for the first case, you can see it's just one time. If you want to have a very stable result, this iteration or this code can be written so that for each of this number of observations, it's going to iterate it maybe 1,000 number of times and take the average of accuracy for each of the group. But this is just for an illustration. So for those that are familiar or want to dwell into multivariate and some techniques, so this is a way of comparing. Now, I'm going to vary the magnitude of difference between the 2 variance covariance matrices, assuming I put 2 instead of 1. So this 2 means that the variance covariance matrix of second population is twice larger than that of first population. And let's see what the result will give us if we do this. So this is the output. You see that when the variance covariance matrices are not the same, the linear seems to perform woefully. The performance is getting not as good as that of quadratic, because quadratic is the assumption for linear is that the 2 variance covariance matrices are the same. So if they are not the same, that method seems to break down. When I say break down, seems to not perform, or it's lost its efficiency. It's better I use that word. So it's going to lose its efficiency when the variance covariance matrices are not the same. While that of quadratic performs better when the variance covariance metrics are different. When the variance covariance metrics are different. So the quadratic discriminant analysis seems to perform better than the linear discriminant analysis. So we may want to vary this different argument that we provided. So if I want to use equal sample size, I will change that the last argument to 0.5, and we have this. And if I want to vary the number of variables or the number of simulations that I want, instead of this just 20 different samples, if I want 30, so I can have this. So we have that, and so on and so forth. So this is by way of comparing, what do you call it, linear discriminant analysis as well as quadratic discriminant analysis. Now, the next thing we are going to look into is we want to look at I thought I didn't have this one. I intend to compare these two with the logistics and linear regression. I want to compare with logistic linear regression, but because of time, I will not know if I can quickly write that code, and so that we'll be able to compare the three, the linear discriminant analysis, the logistics regression analysis, as well as the quadratic discriminant analysis. Let me see if I can quickly replicate the code. The challenge we are having is that in logistics and linear regression, it only recognizes 0 and 1. Let me, if the time will permit me, if I can quickly do the coding for that one so that we will see. So I'm just going to change this one to 0 because it only recognizes 0 and 1. That's for logistics regression. So let me say fit underscore log GLM. You are still going to say group is equal to dot comma family is equal to binomial, then data is still our data. So we have that. Then we are going to say, let's say press first. So this press will first predict the probability. Predict our fit. If I'm still on, Adiola?
Yes, sir.
Yes, sir.
Okay. So I'm trying to build in the logistics. So let me quickly build that so that we run that and see. So we have predicted, let me say predict 3 will now be if S if S my press is greater than 0.5, that should be 1, 0, otherwise Just hope I'm not missing out anything. Then now ACC for, let's say, lodge, you now the sum. Let me just repeat this. Dot log. You now do this. You click 3. Then this. Then high is equal to ACC underscore log. So this comes log column to the 4. So let's try this if it's going to run. I just try to add logistic to our function. And let's see if yes. Okay, let's try it. So IDA underscore QDA underscore log. To find the arguments. The arguments are, the first one is the row. That's the correlation. The next argument is P. Let's say we have 3 variables. Let's our M to be 1 and our K to be 20. This is equal proportion. Good. So we try to compare. We just added binary logistics because in multivariate in statistics, we use that techniques to also classify our individual, our observations into groups. The only limitation is that is only for 2 groups. It's only for 2 groups that you can use binary logistics for, that is 2 populations. And specifically, we have to use 0, 1 as our response variable or the grouping variables. That's why I edited that code. Instead of using 1, 2, as I've used it for LDA and QDA, I quickly changed that code to 0, 1, as we have seen. Now, we added the logistics to it to see how good it is compared with the previous 2. As we all know what binary logistics is all about, and so on, that is when the situation in which our response variable is no longer continuous, it's categorical. So that's the idea that we use and binary logistics, that we can also use it for classification. And the result, as we have seen on the screen, so we see that in most cases, both binary logistics and QDA seems to perform better than what do you call it, the linear discriminant analysis. So, but as I've said, this simulation that I did is just 1 point output. If you want a very stable result, so we need to do this iteration maybe a several number of times, so that we'll be able to say that yes, we are guaranteed that this result is very stable, that if you do it any other number of times, these are the likely result that we get. But this one is just 1 point case. That is, when I take a sample size of 10 and I apply the 3 model, this is what I have. So what I mean by simulation is that for stability is that when I take that 10, I can iterate it maybe 1,000 times and get the accuracy for it this 1,000 times and take the average. So that will give us stability. That will give us stability. So to quickly write that code, I may not have the luxury of time to do that. So that is we can vary this the parameters to get as different result as possible for easy comparison that we may want to do, either when the failure parameters are the same, either we use equal number of sample size for each groups, or even for a number of variables, when P is 2, when P is 3, when P is 4, and so on and so forth. Even the correlation, assuming that, let's look at this, assuming that relationship between the pairs of variables is like they are almost independent of one another. What are the likely outputs that we may want or we may see? So here, I've changed that my row to 0, approximately 0, and I'm still using my number of variable P to be 3. Let's see what we have here. So you see the output here. Here we are saying that the classification variables are kind of almost independent of one another. And here is the output as we have seen. So these are the various things that we can do if we are dealing with multivariate analysis as regarding classification analysis using R. I don't know if this thing is stable so that I can quickly install this package and take us to the second practical. Let me try it again before I call it a day, so that if you have questions to ask, we will allow the participants to ask their questions. Let me try it for the last time again, if this package will load.
All right, sir. Thank you. So please, if you have questions, please drop it on the chat. And for those online, please drop your questions online so we can read it to talk. So the recording is live on YouTube. So in case there's a part in which you are working on along the line when Prof was talking, you did not get, please always refer back to the video and watch it, and let's practice some of these things. Sometimes if you don't practice, you might be locked out sometimes. So practice makes perfect. So let's wait for, so once Prof is done, you can always ask him these questions. Please drop your questions on the chat of the call. So Prof section is live on YouTube, and you can always go back and watch it to understand more data.
Let me select another maybe one that is giving us problem. I'm so sorry that I thought that package is already installed in this particular laptop. It's quite unfortunate, the MV test package, because without it, we cannot run the test of hypothesis that I should have taken us through. Okay, let's have questions.
Okay, thank you, sir.
This one we load for the last time. It's going to install. So if you have questions, we can be dropping them so that we take the questions. If this one is installed, you can take this thereafter.
Okay. Okay, sir.
Adiola,
thank you. Yes, sir.
are you still there?
Oh, yes, I'm sorry.
I mean, we can take questions from the
Okay.
participants.
All right,
now.
sir. Okay. Please, if you have any questions, please let's ask our questions while this is running. So, sir, my first question is going to be on this, some of these packages we are installing. So this installation is dependent on some of the codes you run. So what if you don't install it? Is it going to break, or What can be the limitation to not installing these packages, please?
Yes, as we are all familiar, as we all know with R, some of the modules, some of the functions are package dependent. So if the package or the packages are not installed and loaded, the code may not run. The code may not run. So like this one that I want to do for testing for test for hypothesis, without that NV test, so the code that I've just written will not run, will not work. So most just that's the would I say the funny thing about R, if the appropriate packages are not loaded, so your function may not run. So I don't know, maybe it is the wrong the CRAN that I choose. Let me choose another CRAN.
Okay. So while we are waiting for that, there is a
But
question.
you can still be entertaining as many questions as possible while we are, yes, if
Yes,
there
so
are still more questions. So I don't know if I've attended to your question.
okay, so I'll read out the next question for you. Are you with me, sir? Okay, so the
Yes,
next
I'm with
question.
you.
Okay, the next question says, when working with a real data set, what should be the appropriate sample proportion to use for the trained data set? Can I take that again?
Take it again, please.
When working with a real data set, what should be the appropriate
Can you come
sample?
again?
Okay, when working with a real data set, what should be the appropriate sample proportion to use for the trained data set?
Okay. It is advisable that the proportion of trained data sets should be more than that of test data sets. So for instance, you may decide to use 75% for train, while the remaining 25% for tests. So the worst scenario is using equal, but avoid your test data to be more than trained data sets. That is, let me repeat myself. Always avoid your test data set, the proportion of it, to be more than the trained data set. The trained data set should be more than the test data sets. Thank you.
All right, thank you, sir. The next question says, also at the theoretical explanation for hypothesis, for the alternative, must it always be a two-tail?
Thank you. It's not necessary that it must be a two-tail. It could be directional, that is one tail. It's not, it depends on our study or what we are researching on. If our research necessitated using two tail, so be it. But if one tail, so be it. But it's not a must that the alternative should be two tail. So it depends on the objective of our study, what we are trying to achieve. So it's not a must that it must be two tail. Thank you.
Okay, thank you, sir. So the next question says, the cutoff used in the binary logistics was 0.5. Is it generic or there is a statistical meaning or statistical means of getting the threshold?
Thank you. You see, in binary logistics, when we predict the values, because our response variable, which is our dependent variable in binary, is lies between 0 and 1. That is a value of 0 and a value of 1. Now, a value close to 0 means that that particular prediction is tilting towards 0, while a value is close to 1 also is telling us that that particular observation is tilting towards 1. Now, to answer this person's question, is that we use 0.5. We are trying to be objective, that if we use 0.5, we know that any value that is above that threshold, let's say 0.5 and above, so it's more than half. So we can say that that particular probabilities could be approximated to be 1. While values less than 0.5 could be said that, okay, this could be approximated to be 0. Now, what I'm about to say depends on the research you are doing. If it's about those in the health sector, what have you, that we are dealing with human beings, that we don't have to play with life of individual. So we may change that cutoff of 0.5 to, let's say, 0.75. That is, we wanted to be kind of very sure, very certain that this value is actually very close to 1 before we can say that, okay, this is 1. But conventionally, what we have to use is 0.5 if you don't want to be subjective. Objectivity of this is that the moment the value is 0.5 and above, it can be approximated to be, that probability can be approximated to be 1. And the moment it's less than 0.5, then that probability can be approximated to be 0. So that is the reason why we are using 0.5 as the cutoff in the case of binary logistics. Thank you.
Okay, thank you so much, sir. So the next question says, okay, we have Mr. I don't know, apologies if it's Dr. or Professor, apologies. So that's Sunny Abdullah Adamu. Thank you for this wonderful presentation. I really appreciate it. Then, okay, so we have another question from the online team or the online attendees. So someone said, are you with me, sir?
I'm with you. I'm with
Okay.
you.
All right. So what if our population variable is not normally distributed? When working with a real data set, what should be the next line of action, please? Did I take that again?
Thank you. Yeah, I got the question. I got the question. When I was explaining on that theoretical approach, thank God that that's questionnaire, that person that asked question, damn it, follows the presentation, because one of the assumption was that our data matrix, our X, is assumed to be multivariate normal. This efficiency, when the data is not follow or does not follow multivariate normal, they seem to lose their efficiency. I want to even plead with the coordinator of this UNILORIN R User Group to probably create time for me so that we'll be having this thing on a regular basis, so that we'll be taking ourselves through some techniques in multivariate using R. So what I'm about to say is that we would have compared situation in which we are going to simulate from different distribution apart from normal and compare the results. So we are going to have results, good, but are we going to have a better classification technique or rule or outcome in terms of level of accuracy or whatever criterion we want to use? No, we are not going to, because if this assumption fails, that's LDAQ they were going to run. They are going to have classification. They are going to, but they are going to lose their efficiency. So, and that calls for what we call regularized discriminant analysis. There's another that is a bit robust to some failure of our assumptions that I've just talked about. So we call it regularized discriminant analysis. So that technique, we try to um, overcome the deficiency or the failure of this assumption. When I was running the code the other time, when my number of variables is greater than, sorry, yes, it's greater than the number of observations, you see that the code gives error, it gave error message that the QDA, the quadratic, will not run. If I may explain this, under LDA, linear discriminant analysis, if I have 10 observations, in which there are 5 observations in group 1, 5 observations in group 2, and number of variables is, let's say, 6, and number of variable B is 6. You know, number of variables is 6 is greater than number of observations in group 1. It's also greater than number of observations in group 2. But LDA will run. QDA will not run. The reason is this. In LDA, linear discriminant analysis, is going to pull the variance covariance matrix because it's assuming that the variance covariance matrix for group 1 is not different, it's the same with that of group 2. So it's going to use common variance for this discriminant function, common variance. And in using common variance, it's going to use the N1 plus N2, that is 5 plus 5, which is going to be 10 observations. And that 10 observation is greater than 6, the number of variables. So that is why in LDA it will run. But when you get to QDA, quadratic discriminant analysis, it will not run. In quadratic discriminant analysis, is assumed that the variance covariance matrix for the two groups are not the same. And it's going to estimate their variance covariance matrix separately. It's going to get the variance covariance matrix for group 1, going to get the variance covariance matrix for group 2. So in getting the variance covariance matrix for group 1, in which the number of observation is 5 and the number of variables is 6. So the number of variables is greater than the number of observations. So definitely the variance covariance matrix is inestimable. That is why the QDA is not going to run. But the regularized discriminant analysis will run because it's going to use another method of estimating the variance number of observations. So back to the question. Yes, they are going to run either IDA, either QDA, even the regularized, it will run, but the efficiency will reduce. They are going to lose their efficiency. What I mean by efficiency is that the accuracy, the level of accuracy will reduce. So if it is multivariate normal, maybe the accuracy is, let's say, 0.8 for LDA, let's say multi 0.7 or even 0.5. And for QDA, it may drop, let's say from 0.9 to 0.7 or to 0.8. So that is what I mean by efficiency. So thank you.
Okay, thank you so much, sir. Thank you. Yes, I think that's the last question we have from the attendees online. Thank you so much, sir. For those wanting to join the WhatsApp
Once
group,
again, I want to apologize for that. I want to apologize for the other aspect that are supposed to have taken us through. The network here I'm using at home was so bad, so I was unable to download the needed package for that test. I believe that the R Users Group coordinators will find another time
Okay. Well, so I think that is the network problem. Yeah, so thank you so much, Prof. That was an amazing session. Thank you for treating our questions. And yes, Prof, we will definitely have you again. This session was amazing and was quite
to have this maybe one or two platform, and I would say more well to the speaker in this very on.
all right, sir. Thank you. Definitely, we would love to have you back, and which is definitely going to happen. So be expecting our call, sir. When we call you next time, please you should accept our call, sir. Thank you so much, sir. Please, if you want to join the WhatsApp group, the link is on the chat of the call online. And for those online, the link is on the chat of the YouTube live. So please, you can always go there and join the WhatsApp group. And you can ask your questions, like the code of conduct when asking our questions. Please, let's be respectful with our questions, please.
Platform.
Very important.
I'm not taking it for granted. Thank you once again.
All right. Thank you so much, Prof. Thank you, sir. Thank you, sir. That was an amazing session. Thank you. So please, like I was saying, let's be respectful with our questions, and please let's ask our appropriate questions in an appropriate way. So we can always have someone that will answer us. So drop your questions and we'll definitely have answers for you. Thank you for joining today's session, and do have a great weekend ahead. If you don't have any question for us, we want to say thank you to Professor Gafar for having us, for joining us in this amazing session, for teaching us also, because that's what teacher does. So thank you for teaching us, sir. For Dr. Garba, thank you for hosting us. It was an amazing session. And to all the hosts, we want to say a very big thank you. To all our attendees, thank you so much for joining us. We really appreciate it. So, Prof, we'll be expecting you one more time to come back to us. We don't mind. Thank you so much, sir. Thank you, everyone, for joining, and have a great weekend ahead. Thank you. Bye, everyone.
Thank you, Diola. Thank you, Professor Yemi. Bye bye. Thank you. It was
Bye.
an
Bye,
amazing day.
everyone.
Bye.
Thank you so much, sir.
Thank you. Bye.